Good evening, everyone. Today we will discuss about the bio oil and biochar production. We will discuss thoroughly about the characteristics of the bio oil. That we will not discuss in details of the characteristics of the bio oil because we already discussed in the last class in details. We will mostly focus primarily on the production characteristics and applications of the biochar in this lecture and the processes of biochar production. We will also touch on the topics of bio oil production as well as its applications. So we already discussed that there are so many of technologies that we can convert the biomass to different kind of biofuels, right? So there are already we have discussed thermochemical methods, biochemical methods, and mechanical processes as a pretreatment as well as the conversion technology, which has been followed for converting the various kinds of lignocellulosic biomass into biofuels, bioenergy, and other biomaterials. So, in this lecture, we will mostly focus on the pyrolysis. Is one of the important thermochemical technology that will produce the bio oil as well as biochar in their product, which can be further upgraded into variety of the value added products. Now we will focus mostly on the pyrolysis in this lecture because our lecture will discuss about the biochar and bio oil production. So these two product we will get simultaneous production from the process of pyrolysis. So there will be different kind of pyrolysis processes according to the heating rate variation. So depending on the variation of heating rates, there will be uh, percentage of wise yield variation of bio oil and biochar. There we will mention other processes also that will also help us to convert the biomass sources into biochar or bio oil consecutively. So, biomass pyrolysis, which has been recognized as a potential alternative technology to generate carbon negative fuels or carbon neutral fuels, which will also help to reduce the burden of the fossil fuels on the environment. Now, there are other technological advancement. We will discuss one by one. That there is mainly the concept we have discussed, I guess, in the last few lectures that pyrolysis we had touched the topic, but there are other technological advancement like autothermal or microwave pyrolysis or hydropyrolysis. We will discuss these topics for the in target of discussing the bio oil and biochar production. So the products obtained under these conditions of these the advanced methods that will be giving us a better property of the products than the conventional pyrolysis products. Biochar and bio oil, which we are producing from different biomass sources, that has initial moisture content variation, right? We already discussed from the very first class of the of this series that there are a lot of variation of the initial moisture content of the biomass. So, depending on the initial moisture content, we need to select the appropriate thermochemical process if we want to convert the biochar and convert the biomass into biochar or bio oil to the existing thermochemical conversion technologies. So, in this picture, you can see like when we talk about the existing technology, which will give us various product, which will give us heat along with the various products, like we are talking about bio oil, biochar, and also there will be syngas production, right? So there is temperature scale, and in the right hand side vertical axis we can see the oxygen supply. It is also an important factor for the different process condition. So when we are talking about combustion process, this is also a thermal process that will be operating around 900 to 1500 degrees Celsius in the presence of sufficient oxygen presence, right? So when there is sufficient oxygen present, so we are getting mostly biomass energy to heat energy, or thermal energy we are converting directly. So when we are talking about gasification process, which is a thermochemical process that will be operating in the partial oxygen presence or insufficient presence of oxygen. So there are other varieties also, like conventional gasification, steam gasification, and supercritical water gasification. Mostly we get product yield, that is the maximum yield of the product out of the gasification, that is the syngas production. But there are very limited production of biochar or bio oil through the gasification process. So when we want to convert the biomass sources into the gaseous product we are expecting, then we will go for the gasification process. So depending upon the our desired product, we will choose the process wisely, and also depending upon the feedstock characteristics. So when we are talking about liquefaction, we will get mostly the liquid product or the bio oil product. Here you can see there is a variation of the temperature of the process condition. So when we are talking about pyrolysis, there are certain categories like slow pyrolysis, fast pyrolysis, catalytic pyrolysis, microwave pyrolysis, and another one is categorized as flash pyrolysis. So this pyrolysis, this thermochemical operation is generally operated around 400 to 800 degrees Celsius. Now coming to torrefaction, this pyrolysis we will get, obviously we will get, depending upon the category of the selection, we will get the three products, biochar, bio oil, and gaseous product. But depending upon the heating rate of the pyrolysis condition, we will get different yield percentage of these three product. Coming to the torrefaction, this torrefaction technology we didn't discuss earlier. So this is kind of a slow pyrolysis process where we mainly focus to generate the solid product or the biochar production. It is a very it is a very low temperature process, like 200 to 300 degrees Celsius, and we will get the carbonaceous solid material as a maximum yield of the pyrolysis product. To the carbonization, it is also a slow pyrolysis process. It is operating at 400 to 1000 degrees Celsius, and in this process we will also get mostly that biochar or the solid carbonaceous material. And the main difference is, in the carbonization process we will get less yield of the biochar but high energy density. So in the torrefaction we will get a lot of production of the biochar, whereas in the carbonization we will get less production of the biochar, but that will be more energy denser in nature. So this pyrolysis, torrefaction, carbonization, that will be operating as a in the absence of oxygen. So you can see this biomass can be converted into different target product and other byproduct, which has been uh, mentioned in this picture. We are talking about the slow pyrolysis. That reaction may occur in this range are quite flexible depending upon the process you are choosing. Like slow pyrolysis, it can be from 300 to 900 as well. Okay, so in the slow pyrolysis, the target product is mainly biochar, but there are other byproducts also like bio oil and combustible gases. Coming to the fast pyrolysis, where there will be faster heating rate, the condition reaction temperature around 350 to 700, obviously in the absence of air in both of the cases. But in the fast pyrolysis, we will get the target product of bio oil, and there will be byproduct, that is the biochar and combustible gases. So this is, you can easily recognize that when there is faster heating rate, there will be more formation of the liquid product or the bio oil. Coming to the gasification, which will be the process condition is maintained in the insufficient or partial presence of the air or oxygen. The reaction temperature is quite high, higher than the pyrolysis, like 700 to 1200 degrees Celsius. And the target product is syngas. Here we mostly produce, or we mostly get these combustible gases, syngas. And byproduct like we get biochar and tar. Torrefaction, which is also categorized as slow pyrolysis process, it is operating at a very low temperature, comparatively 200 to 300 degrees Celsius, where the most target product is biochar. Other product we don't get because we generally just do the solidification of the biomass or the waste product. Through torrefaction, we get the solidified and energy densified biochar. Generally, other products are not achievable in this process. So we were talking about a biochar production. We already discussed what are the major processes we follow for the biochar production, right? So a biochar, which is produced by thermochemical conversion processes. We discussed a little bit about the pyrolysis torrefaction, and we will also discuss the hydrothermal carbonization process. So there are this carbonization process, it can be in absence of the hydrothermal condition or in presence of the hydrothermal condition. In both of the cases, we will get the biochar and hydrochar respectively. So we will convert the biomass through this process of the pyrolysis in the absence of the air in the range of 350 or 700 degrees Celsius. So we produce a biochar as a carbon rich solid residue with carbon content ranging from 65 to 90 percentage. And this biochar, it contains the surfaces with high level of the aromatic species, as well as it has oxygen functional group on the surface of the biochar, and also it has a good porous structure. This biochar yield from the aquatic biomass, just like algae or other kind of aquatic biomass, they have higher yield of the biochar when it is compared to the yield from we get from terrestrial biomasses. So given that aquatic biomass, they contain higher fixed carbon content and also higher content of the ash. So as a result, we get the biochar yield as maximum when we use the aquatic biomass as our feedstock. Elemental composition of the biochar It changes with the pyrolytic process parameter like pyrolytic temperature, and this composition of the biochar, it also depends on the type of the feedstock you are using. So the carbon content, it tends to increase when we increase the pyrolysis temperature. While there is increase in the carbon content, we get a decrement in the other content like nitrogen, sulfur, hydrogen and oxygen. And these elements evolve when we increase the pyrolysis temperature as a form of gaseous product. So feedstock carbon is modified during this heating process to produce more aromatic rings in biochar structure. These aromatic rings, which are present in the biochar, that cannot be easily degraded by the microorganisms. Thus, we facilitate long-term carbon sequestration possible in the soil. Thus, this biochar produced from biomasses feedstock, different feedstock, we will help to long-term carbon sequestration. Then high content of the lignin in the biomass sources, which will have positive effect on the quality of the torrefied biochar, torrefied in the range of 200 to 350 degrees Celsius. And this low temperature slow pyrolysis process, when there is high content of the lignin, there will be good quality of the torrefied biochar. This hydrogen by carbon ratio larger than 0.7 suggests poor quality of biochar, so we need to maintain less than 0.7 the H by C ratio so that we can categorize this biochar as a good quality. So this biochar has lot of applications. We will discuss further slides. So its application includes soil improvement, carbon sink, water treatment, and kind of we can also use for feed to the other like animals, and fertilizer we can use. So in addition of that, biochar is also used as a precursor material to produce activated carbon and carbon quantum dots. These both a biochar and activated carbon, they are widely used as a adsorbent or filler to manufacture different kind of composite. So as a if we produce activated carbon by the or biochar, we can use like that. So we will produce um, this good quality of the composites out of this. So biochar, which is produced from biomass, has lot of application and lot of opportunities to be used these biomass sources. So I would like to add one point that when we talk about the waste management, so different kind of waste, we can also convert those waste to the char product, and we can also utilize those char in these applications. Like in this application, we can also utilize. So this biochar production is also a motive of waste management overall in the society. As an it can be considered as an option. So carbon content, bulk density, carbon stability and volatile compound content, also the surface area, nutritional content, heavy metal content, pH value, water and ash content, and pH, water holding capacity, porosity and different kind of thing. These all are should be measured as a quality characteristics for biochar. So we will now discuss about the slow pyrolysis processes, mainly torrefaction and carbonization because it has the higher yield of the biochar. So, slow pyrolysis, which involves producing biochar at the range of 300 to approximately 700 as well, with a heating range 6 to 48 degree Celsius per minute under anaerobic condition or in the absence of oxygen. Now, torrefaction, it temperature range is 200 to 300 and carbonization is slightly higher, 300 to 400 degrees Celsius. These are categorized as slow pyrolysis process depending on the temperature range. So, torrefaction and carbonizations are thermal decomposition processes which produce carbon-rich product like char with high energy density, brittle in nature, and also has higher hydrophobicity and reduced H by C and O by C ratio. So these reduced ratios are actually required for a good biochar character. So in these processes, organic substances are heated in inert atmosphere, usually at atmospheric pressure condition, which generates both condensable and non-condensable gases along with the char. Now the solid product or char, it generally contains carbon concentrating residue and mineral components of the raw material. While the gaseous product, whatever we get, it composed of water, carbon dioxide, carbon monoxide and several organic compounds which they form and they release during the process. So ultimately, we get residue as a solid carbon residue as char. So different structural compositions of the biomass that determines the temperature region of the torrefaction. So it has been noticed that biomass with a high content of the hemicellulose is preferably subjected to light torrefaction, like 200 to 235 degrees Celsius it got torrefied, where there is higher content of the hemicellulose. And when we do strong torrefaction in the range of 235 to 275, it mostly beneficial for the higher content of the cellulose and lignin. So in general, when we talk about carbonization process, it is the same process just like torrefaction, but the thing is the carbonization process contributes to more energy dense fuel in compared to the torrefaction process, as in the carbonization we will get less amount of the solid product by this route. Slow pyrolysis without oxygen produces more charcoal than fast pyrolysis or gasification process. That's why we are more focusing on slow pyrolysis process for the production of the biochar as their main or target product. So we will now discuss about the important factor, that is important process parameter, that is pyrolysis temperature, which has great impact on the biochar characteristics. So the thing is pyrolysis temperature, which is a primary factor that controls the degree of devolatilization of the biomass. When the biomass is initially heated to 160 degrees Celsius, there will be first elimination of the free and bounded water content of the biomass. Then when we slightly increase the pyrolysis temperature, there will be initiation of the thermal biodegradation with volatilization of extractives. Then hemicellulose, which is a major stable polymer, it got degraded in the temperature range of 220 or to 315 degrees Celsius. Then it comes cellulose. After that, it cellulose got highly polymerized and they show the higher stability. So they got decomposed in the range of 315 to 400 degrees Celsius. So, and at the last, which is lignin, is the most challenging compound of or element in the lignocellulosic biomass. They got pyrolyzed due to extensive decomposition temperature gradient in the overall range of 160 to 900 degrees Celsius. So we can see with the increase in temperature, the aromatic structure in the biochar, it got increased in both size and quantity. So with the increase in pyrolysis temperature, the availability of the major structural components and other macromolecules of the biomass in the solid residue, it got decreased. So it also decreased the polarity of the biochar. So as we increase pyrolysis temperature, the biochar got more hydrophobic in nature. So the hydrophobicity of the biomass, it increases with temperature to certain extent, but if we increase the temperature beyond suppose 900 degrees Celsius, then again the hydrophobicity will decrease with the increase in temperature. So irrespective of the type of the feedstock that you are using, an increase in temperature increases the surface area of the biochar greatly. So when we go above 900 degrees Celsius, the number of pores in the biochar that we are talking about, that surface area is increasing. But when we go beyond 900 degrees Celsius, the number of pores present in the biochar, they got reduced. Why it is got reduced? Because there will be pore expansion, or the pores, there will be collapse of the pores with the adjacent pore, so the available open pores will be reduced. And in addition with that, the secondary reactions between the volatiles and the coke may result into a collapsing of the micropores. Thus, the micropores got blocked, and ultimately, as a result, we get reduced surface area of the biochar. So, pyrolysis heating rate as well as the residence time of the process, it will influence the yield and the structural properties of the biochar. Is there any question? Sorry, my net got disconnected for some time. Yeah. Is there any question till now? Okay, so we were discussing about the biomass characteristics which will be affected by the variation of the process parameters. So we will now discuss. We have discussed how the pyrolysis temperature variation will affect the biochar quality. So there will be other effects on the other process parameters on the biochar characteristics. So, biochar properties can be tailored by adjusting different feedstock type, heating rate, residence time, other activation methods, and gas environment. So, when we talk about the feedstock composition, lignocellulosic biomass, they produce biochar with very high carbon content and comparatively stable structure. When we take the manure or sewage sludge kind of feedstock, we get high ash content and nutrient content, which is suitable for the soil applications. Agricultural waste like straw or husk, they produce moderate porosity and nutrition, which will be redundant and a good quantity in the produced biochar. Now, algae and aquatic biomass, they also produce mineral content of the biochar but low carbon stability in the biochar. So most stable and more highly carbon content of biochar we can produce using the lignocellulosic biomass. So we already discussed that how that a slower heating rate that will promote complete carbonization, which will lead more structured and stable nature of the biochar. A longer residence time will increases uh, the biochar stability, but it may reduce the yield of the biochar due to excessive carbon loss. This pyrolysis atmosphere, it is also having an important role on the biochar characteristics. Now, when we do inert atmospheric condition, then the biochar produced will have stable carbon content. When we do in the presence of steam or in the presence of the carbon dioxide atmosphere, it will enhance the biochar porosity and it will also enhance as a result the surface area of the biochar. Oxygen and air, that will lead the presence of oxygen and air, if it is present in the pyrolysis condition, that we generally don't consider, but if still if the oxygen is present, then it leads to oxidation and reduce the biochar stability. So that's why when we do the pyrolysis reaction, we must ensure that there is no contact of the oxygen during the during this thermal conversion. So now we will talk about the advanced technology which has been used for pyrolysis or product as a advanced pyrolysis method, that is the microwave assisted pyrolysis. So it is obviously a very efficient method in terms of heating of the biomasses and converting the biomass energy uh, into utilizable energy from the homogeneous source of waste. So this method is amongst the ultimate attractive alternative for speeding up and optimizing the chemical reactions. So due to excellent heat transfer profile that we follow in the microwave assisted pyrolysis, the chemical reactions are performed quickly and efficiently compared to the other thermochemical processes. So the microwave assisted pyrolysis they provides several benefits compared to the traditional pyrolysis, including uniform heating altogether. If your um, feedstock is homogeneous, so there will be more chances of the uniform heating and a quick heating rate, volumetric and selective heating they provide in the microwave assisted pyrolysis. So this microwave heating they simplifies the process with rapid on off control and increases the product and quality production. So it limits the hazardous product development, pollution output. Also it makes the procedure environment sustainable. Additional benefit of the microwave assisted pyrolysis is there is rapid heating efficiency due to in situ heating method that we are following in the microwave assisted pyrolysis. So the capacity for handling the wet biomass without drying we can do, and also the potential to pyrolyze the enormous biological molecules we can do without any issue in the microwave assisted pyrolysis process. So what we do here, they transfer the energy rather than heating of the biomass. They transfer the energy in the sense of electromagnetic energy, which is being transformed into heat energy by the conductive heat transfer. Also, the energy which is released within the biomass volume in the operation of microwave assisted pyrolysis, that is being done um, in the biomass volume rather than we external source we are supplying. So in this picture you can have an idea that how this microwave heating is different from the conventional heating process. So in the conventional heating process, suppose this is a biomass molecule, so we are doing the heating at the surface of the biomass molecule. But in case of the microwave heating, we are passing through electromagnetic energy which will um, transfer the energy into the volume of the biomass. So the temperature of the biomass center got higher than the temperature of the surface. So thus it goes from inner to outerwards. Thus way it is different from the conventional heating, and as we are doing in a volume biomass volumetric way, so there is uniform heating expected in the microwave heating process. The uh, the condition is given that the feedstock should be homogeneous in nature so that it uh, assists the uniform heating. So the microwave biochar has unique physical and chemical properties, and it is very stable when it is compared to the conventional pyrolysis method. Compared to the previous heating process, the feed here in this process is heated from depth of the sample to the surface of the sample. That is, inner of the sample, it slowly goes to the surface of the sample. Thus, it allows the heating process to occur at a very rapid rate. Microwave heating is very quick and energy efficient heating process. It facilitates yield production, eliminates the need for liquid convection. It also facilitates good way thermal control, restores the energy and chemical value of the waste products. So it has the best biochar production in terms of quality, and it is also efficient method in terms of the surface efficiency and cost effectiveness. So here the resulting biochar will have the higher surface area, approximately 450 to 800 meters square per gram, and it also contains many functional groups on the surface of the biochar when it is compared with the conventional biochar produced. So you can see that in despite there is lot of advantage that we are discussing about the microwave assisted pyrolysis, there are certain limitation that we also need to discuss. So let us first discuss the benefits that we can summarize from here. Volumetric and selective heating, they are economic in terms of short time and high efficiency. We can also have the control over heat in a proper way. Instant on off control we can get, and also this is environment friendly process. But the limitation it has that poor microwave absorbing material. If the material or the biomass sources that we are using, if it is less conductive in nature, then there we have to give more power to absorb, to help the biomass molecules to absorb the microwave energy. And in some cases we can see, and also this microwave energy they can absorb depending of their dielectric properties. So we can see there is kind of random heating that also that also creates an issue because of the creating hot and cold places. Because in some of the region, suppose we are taking a biomass molecule, and in some of the region of that molecule they absorb more energy. So if it absorbs more energy, they will be heated up very faster way, and they further increase the possibility of getting creating the hot spots by overheating that spot, and other places will be relatively cool in nature. So there will be random heating profile that will generate. That may be a limitation some of the times in case of the microwave assisted pyrolysis. Also the arc and plasma form due to thermal runaway condition. This thermal runaway condition is also like if the system contains conductive materials like some metal contaminants, then there will be high energy microwave interaction can generate between the electric arcs, which can damage the equipment as well. So we need to ensure the pre-treatment or the separation of other impurities before this biomass sources is introduced to the microwave reactor. And also it it should be mentioned that there is relatively complicated reactor design for the microwave assisted pyrolysis process that we are talking about. So here there you can see some visual schematic. You can get an idea that how the pyrolysis reactor acts or behaves. First one is the microwave pyrolysis. You have seen the microwaves, right? Microwave we use for the cooking purpose. In the same principle or the same kind of reactor we use for the microwave pyrolysis reactions. So you can see there the inert nitrogen gas is passed through and the volatiles are collected from the other outlet, and the microwave energy is passing through the biomass placed inside the reactor, and that will help to get the faster heating rate, and that will convert the biomass carbonaceous material to the carbonaceous material or other volatiles. Second one is the rotating cone. Here we use the sand plus biomass in the reactor, and we will collect the volatiles at the top of the reactor, and this is kind of rotating cone in design. In the next, the fluidized bed, which is used as a widely for pyrolysis reaction. Nitrogen is passed through from the bottom of the reactor. The biomass molecules got fluidized in conditions, and in the presence of the temperature conditions, the biomass molecules are converted into char product as well as volatiles, which are collected from the top of the fluidized bed reactor. Next one is the rotary oven. It is rotating like a rotary kiln at a high temperature conditions. But here we are talking about the pyrolysis, so that pyrolysis temperature range is maintained. For converting biomass, here we are introducing the biomass feedstock and we are collecting char because it is quite of heavy solid residue. It will be collected at the bottom of this um, rotary oven, and the volatiles will be collected from this. So the next one is the ablative reactor. It is kind of new uh, kind of reactor where this in this process we are giving the direct contact between the heated surface and the biomass. So there is direct solid to solid contact that is mentioned in the ablative pyrolysis reactor, and the reactor it employs the mechanical forces to press the biomass against a heated metal surface, and thus it allowed the rapid thermal decomposition. So it is mostly focusing on the solid solid heat transfer, so thus it involved rapid thermal decomposition. Next one is come, it is the agar pyrolytic reactor, where you can see a screw is there inside the reactor, that is the heating zone. Biomass is introduced and it is the screw is like rotating in such a way, and the solid fractions are collected at the bottom of the reactor. So it is also the principle is like that the rotating screw, which is called the agar, and they move the biomass through a heated reactor in the absence of the oxygen, and this rotating screw, it controls the residence time of the biomass, and also it has this rotating screw, they efficiently perform for thermal conversion. So here we are not doing the direct heating just like the ablative reactor. We are doing the indirect heating by the presence of uh, this mixture heated sand and metal particles that will help to heat the biomasses, and also we are doing also the nitrogen environment is maintained inside the reactor to prevent the oxidative any kind of reaction. Third one is the this last one is the fixed bed. It is also widely used, and the stir tanked reactor. This kind of whole of the reactor that we discussed, this kind of reactor generally we use for the pyrolysis purpose. So sorry. So now we will discuss about some of the comparison between those reactor that we talked about, and also some uh, additional reactor like thermal plasma reactor or vacuum reactor for pyrolysis purpose. So in the pilot plant operation in a bigger scale, we generally use the agar and commercially fluidized bed reactor. So mostly complexity we find in terms of the mixing of the biomass with properly in a conditions. So complexity involved a high fluidized bed, rotating cone, ablative reactor. Also in case of the thermal plasma and vacuum reactor. So at a very high temperature condition, the thermal plasma reactor is conducted, and microwave is slightly lesser than that. When the reactor size we consider, the reactor size is bigger for the vacuum reactor, and the mode of the operation is batch for cases, and most of the cases there are continuous process like rotating cone, fluidized bed, agar reactor, microwave reactor they can be, and thermal plasma reactor they can be both batch and continuous mode. So in requirement of the inert gas that we are talking about, the high inert gas presence is required for fixed bed and fluidized bed reactor, and lowest we can go for microwave reactor, also ablative reactor that we talked about, the direct heating between the two solid surfaces. So the most efficient heating method that we are following for in this reactor, that electromagnetic heating process, and other heating like direct contact with the surface and direct and indirect heating in the fluidized bed. Also rotating cone, we introduce the sand particles and heating that we get from the wall of the reactor. So there are possible modes of direct and indirect contact of heat transfer. The rate of heat transfer is highest in case of the thermal plasma and slow intermediate in case of the microwave. Very slow in terms of the fixed bed condition, and fluidized bed it is also faster. Gas residence time in the thermal plasma, it takes few milliseconds to few minutes that the gas resides into inside the reactor, but in other cases like the maximum time it takes for agar reactor, because the it takes seconds like 30 seconds, and also the fixed bed condition the gas residence time is higher. So you can go through this table of comparison so that you can select that which reactor you should use depending upon your process condition available. Also depending on the cost efficiency of the overall process. Okay. So now we will discuss the other process for char production, that is the hydrothermal carbonization. We already talked about carbonization process as a slightly higher temperature range than torrefaction process, but here we are going to discuss about the hydrothermal carbonization. So how it is getting different, just you see that traditional thermochemical conversion strategies like torrefaction and carbonization can lower the chlorine concentration of the biomass, or you can use the waste product or waste material, but they also increase the ash content since the volatiles are removed in the process. On the other hand, when you talk about the hydrothermal carbonization, they densify the polymeric as well as lignocellulosic compositions, while also it decrease their ash contamination via fractional dissolution in the water. So basically hydrothermal carbonization is a process that occurs at a temperature range of 180 to 250 under anaerobic conditions in the presence of the liquid water or supercritical fluid under elevated pressure condition. So this process, hydrothermal carbonization, they mimic the natural coal formation process but occurs at a significantly shorter time scale. Typically from hours to days, we get the char product. So here, how we are making differentiate, like we are termed the char produced here as hydrochar. This hydrochar, they contain 50 to 90% of the carbon with a good porous structure that will enhance the adsorption capacity of the hydrochar. So this process is characterized as a deep degree of the impact on the feedstock, resulting in a higher quantity of the carbon product as well as higher quality. So this is known as, also we can refer as biocoal or hydrochar. So longer hydrothermal treatments, they contribute not only an increase in the calorific value of the hydrochar, but also they produce the material with more complex structure associated with the polymerization of the intermediates those are formed. They got the polymerized and they ultimately formed a good quality of hydrogen. But some of the times when we get a good amount of the a good quality of the hydrochar, the yield of the hydrochar got reduced. An increase in the reaction time, they contribute to the formation of certain porosity of the structure. So an increase in the pore volume and a higher surface area we get when we increase the reaction time. So during the hydrothermal carbonization process, biomass undergoes a series of the complex chemical reactions including hydration, decarboxylation, polymerization. Hydrochar, it is rich in oxygen containing functional group, thus it promotes the higher reactivity of the hydrochar. Hydrochar, which can be also used like biochar in the soil treatment process, energy storage like manufacturing of the electrodes, and water purification process as a good adsorbent. The advantage of the hydrothermal carbonization is that without any energy intensive drying method that we follow, we can transform any kind of biomass with any quantity of the initial moisture content. We can form the carbonaceous solid by the this method, hydrothermal carbonization. So we are not restricted to any um, kind of restrictions we are not following for initial moisture content of the biomass, because we are not requiring any kind of dried biomass. We can directly go with the wet biomass and we can produce the carbonaceous material in the presence of elevated pressure and temperature condition. So these are the four steps that we follow in the hydrothermal carbonization process. We can operate like biomass with content of 75 to 90% moisture, initial moisture content. We can easily process this biomass in this hydrothermal carbonization process. So first we go for the hydrolysis, where biomass components such as cellulose, hemicellulose, lignin are hydrolyzed into smaller molecules in the presence of the high pressure water, leading to formation of some sugars, organic acid and other soluble compounds. Next step, it follows dehydration, where the water molecules are removed from the biomass matrix, resulting in the formation of intermediates such like furfuryls, aldehydes and ketones. Next, it follows the decarboxylation process and polymerization, where the carboxylic group present in the biomass components are eliminated and they lead to release of the carbon dioxide in the form, and they also form the aromatic compounds in this stage. Last stage, it follows carbonization, where the continuous heating and high pressure condition, they cause the carbonaceous intermediate to undergo the carbonization process, which result in a production of the solid hydrocarbon. So in this process that we talk about the high pressure condition, this autogeneous pressure is automatically generated the system high pressure condition. Residence time, it follows zero point 0.5 to 8 hours. Very short time we get the carbonaceous material. So the carbon content is increased during this last stage of carbonization phase. The content of the oxygen and mineral matter, it got decreased with a minor gaseous product. So these are the four major stages followed in the hydrothermal carbonization. We will now quickly do the comparison between the biochar and hydrochar. Biochar, which is a high carbon and fine grained residue that we get via mainly pyrolysis process in the absence of oxygen, and it results in the formation of the solid biochar, bio-oil and syngas production. Whereas hydrochar we get mostly by the process of the hydrothermal carbonization and liquefaction process. Here, these two processes, carbonization and liquefaction process, they produce the hydrochar, and when we go for the liquefaction process, it will produce the bio oil. Okay, so these processes involve subjecting wet biomass to high temperature, high pressure condition. We convert the hydrogen. Now, biochar is stable, solid, rich in pyrogenic carbon. It can endure in soil for thousands of years and making it suitable for carbon sequestration, also helping climate change mitigation. Whereas hydrochar it exhibits stability and can persist in the soil. Its refractory nature contributes to carbon storage also long term, but the stability of the hydrochar is lesser than the biochar. But the biochar typically contains a mixture of the carbon as well as impurity like ash and other elements in your inorganic materials. This property depends basely upon feedstock and pyrolysis condition. Whereas similarly, hydrochar also is a carbonaceous composition but may differ in the alkali and alkaline earth and heavy metal content because um, we are using the water presence, so this content may be lesser in case of the hydrochar, and it possesses a larger surface area and higher heating value than the biochar at the same operating temperature. So application wise, the biochar can be applied, or that can have application in the soil treatment to improve the fertility of the soil and giving the nutrients availability, or and also the water filtration. It is hugely used in agriculture, forestry, and environmental remediation application. While in the hydrochar, it is also applied in soil improvement application, just like biochar, and it also explore other application like energy storage, any kind of pollutant removal, because it has also good absorbent capacity. Environmental consider that biochar that can alter the soil pH and introduce the chemical characteristics that impact the microorganisms, whereas hydrochar it also impact the microorganism, but the most explore of its benefits in kind of microorganism impact that yet to be researched, like a matter of research going on. Next, we are going to discuss about the gasification process, because in the gasification process we will get the char as a byproduct, not as a main product. But still we are going to discuss because it also because this process has byproduct yield of biochar, right? So the main thing is this gasification process. They convert the heat from the carbonaceous material with a gasification agent like air gasification or steam gasification, or in the presence of the oxygen at a high temperature and pressure condition of 75 degrees Celsius into biochar and oxygen deficient different stage. So when we talk about gasification, it is taking at a high temperature. So we are getting more cracking of those carbonaceous material, and we are getting more gaseous yield based on the gasification process. So when air is used as an oxidizing medium, the resulting gas they contain 85% syngas, which include hydrogen, carbon monoxide, carbon dioxide, some methane, and other lower molecular weight hydrocarbon. So it is disclosed that the steam gasification mode they yield more hydrogen, which has the higher heating value. Typically, gasification operation consists of four consecutive steps. It involves pyrolysis. It's one of the step includes. So it involves drying, pyrolysis, partial oxidation, and then it follows reduction at a higher temperature region. Biochar yield are insufficient under this gasification condition because we are getting a gaseous product at maximum yield in the process of gasification. So that's what the primary limitation of this process is. biochar is produced as a byproduct, not main product. And there are a lot of chances of the greenhouse gas emission. We can see the comparison of the biochar synthesis method. We have discussed pyrolysis process, hydrothermal carbonization process, and gasification process. So pyrolysis process here low residence time, higher biochar yield. Any kind of organic feedstock can be utilized. We get larger surface area of the biochar, higher conductivity that we can use as a electrode material, and porous structure. Obviously it is environment friendly process, but the main disadvantage that pyrolysis involves, that is the initial moisture content that should be less than 30%, and also it needs inert environment, and sometimes that becomes costly. While we are talking about hydrothermal carbonization process, it is not an energy intensive process because we are eliminating the drying method. Also, any kind of biomass that is having higher moisture content can be processed through this technique, and we can get carbonaceous material as a product. Also, the hydrochar produced by the process had a higher concentration of the oxygen in the surface, so it has higher reactivity. But disadvantage is the carbon stability is lower than the biochar, and there is low toxic substances. In the gasification process, the main disadvantage includes it doesn't yield so much biochar. Obviously, it focused on the higher yield of the syngas, shorter residence time, and it is inexpensive. So we will now discuss about the applications of the biochar in different environmental conditions. So biochar, we are producing biochar from biomass, so it is obviously a cheaper carbonaceous product. It is it has gained lot of interest in such a cost effective alternative to the activated carbon for reducing the number of the organic contaminants from the aqueous solutions and variety of the inorganic contaminants. So, due to exceptional capabilities like high adsorption capacity, largest specific surface area, microporosity, and ion exchange capacity, biochar offers a wide range of the environmental applications. So, coming to the adsorbent, biochar as an adsorbent, it efficiently acts for adsorption of the organic like polyaromatic hydrocarbon or polychlorinated dibenzo paradioxide or isoproteron. So these kind of organic chemicals they can also adsorb or separate, and also inorganic inorganic metal ions they also can adsorb for reducing the pollutant from the environment. Biochar, which is a porous solid with large surface area, it is also a good material for wastewater treatment. It has shown an excellent medium for absorbing the nutrient from the effluent, and it also can be used as a soil modification source. While the largest surface area of the activated carbon that favors the toxin absorption via pore filling or many components like particularly surface functional groups, they facilitate the biochar's removal execution. So biochars distinctive chemical structure such as they contain higher surface area and specific uh, quantity of surface functional group, they simplify generated via activation and functionalization, which is very prominent promise application, as a flexible catalyst and catalytic support they provide in the various chemical reactions. So, by oxidation, biochar may be simply separated from the catalyst to extract the precious metal that are adsorbed. Thus, utilizing biochar as a as a catalyst will increase its use and cyclic capacity. Biochar treated with the potassium hydroxide or sulfonated with fumic sulfuric acid, they exhibits greater isomerization in the biodiesel generation. So biochar can be used as an electrode material that serves at a large surface area, which is inexpensive comparatively, and it is widely having utilization in microbial fuel cell and supercapacitor. Biochar is barely resistant to microbial breakdown due to its more content of the aromaticity, so it benefits soil carbon sequestration. We see that application wise, catalyst, low cost and more significant proportion functional groups are present. Energy storage, they produce the electrode material, but some kind of relatively poorer performance than other electrode that we use, but still we can use as an alternative. Soil amendment, they increase the fertility and quality, improve the quality of the soil, so it increase the carbon sequestration. But benefits is that it is low cost material and reduces the greenhouse emission. Also, it regulates the nutrient loss. But some kind of the presence of heavy metal and polyaromatic hydrocarbon, if that is there inside the biochar, then it may contaminate the soil. In terms of the adsorbent, the organic and inorganic contaminants that can be removed very efficiently by this different kind of biochar adsorbent in from soil as well as aquatic systems. So it offers lower cost and increased oxygen groups in the biochar that improves the absorption capacity of the different contaminants. But sometimes the pollutant degradation effectiveness is limited and heavy metal may retain in the soil for longer time that may create contamination. Also, if we compost the biochar, that will enhance the microbial population structure that will ultimately enhance the carbon mineralization. So, thus they reduce the greenhouse gas emission and they also increase the nutrient value of the soil. We discussed about in detail the characteristics of the bio oil in the last class. So we will now touch mostly the application and advanced process of bio oil production, not in details because we already discussed in the last class. So here the bio oil, which is the liquid produced in the process of pyrolysis, it also has numerous application. So it can also be directly used in the boiler fuel, but it has certain limitation. We need to take care of that. And also it can be used as a raw material to produce different chemical products out of the bio oil. So bio oil production mainly follows fast pyrolysis process, which favors the bio oil yield as a primary product under moderate temperature conditions, shorter residence time of the vapor, and higher heating rate. So, bio oil is composed of a complex mixture of different organic substances like aromatic hydrocarbon, phenols, ketones, ester, ether, sugar, amines, alcohol, furans, and water. They obtained by chemical reactions and biomass moisture. So this bio oil, which is highly oxygenated in nature, the higher oxygen content sometimes it creates lot of issue uh, for utilizing the bio oil directly as a in the boiler condition. And it is for this highly oxygenated situation, it is chemically unstable also. So we need to go for upgrading of the bio oil so that we can reduce the oxygen content and removing other waste. Bio oil, which is having some undesirable features like high acidity, low thermal stability, low heating value, and high viscosity when it compared to the conventional diesel. So we need to go for some upgradation method to improve this quality, which are shortcoming in bio oil. We upgrade the bio oil into biofuels via hydrodeoxygenation, which aims to decrease the oxygen content of the bio oil to increase the heating value as well as to improve the thermal stability of the bio oil. So we are we will now discuss about some of the important operating parameter that will affect the biomass pyrolysis process for bio yield in the target of uh, bio oil yield. First one is temperature. Obviously, the each biomass has potential to provide maximum bio oil yield as a specific pyrolysis temperature. So this conversion efficiency will increase with the increase in temperature because due to the extra energy available to break down the biomass molecules bonding, and we get the higher it studies there are studies they reported that higher liquid yield content we get in the range of 450 to 550 degrees Celsius. But we see that at a higher temperature there is secondary cracking of the volatiles, which results in a higher gas yield. So if there is secondary cracking is happening, so we will have more gaseous yield. We will not get higher yield of the bio oil. So we need to minimize the secondary reactions happening. So beside the yield, the quality of the liquid also varies with the temperature. So bio-oil obtained at a low temperature will composed of alkenes, long fatty acids, ester and aliphatic nitriles or amides. A higher pyrolysis temperature will favor the cracking of these aliphatic species and they form more aromatics resulting in a lower H by C ratio of the bio-oil and higher organonitrogen particular content. Now, the effect of the heating rate. The heating rate of the pyrolysis process, is another crucial factor for biomass decomposition. So we already discussed that fast pyrolysis, while the higher heating rate they causes maximum bio oil yield. The pyrolytic behavior resulting from the heating rate variation can also be associated with the feedstock composition. So, in case of the triglyceride material, a higher heating rate can induce a cracking of the condensable vapors. So, faster heating probably inhibits the secondary dehydration reaction, causing in the reduction of the water content in the bio oil. That's why fast pyrolysis is mostly preferable for the production of the bio oil. The oxygen content in the pyrolysis liquid product is also reduced, possibly reduced in the process of higher heating rate. So it is suggested that the formation of oxygen containing gases such as carbon dioxide, carbon monoxide, it also increases due to the higher heating rates. Next one is the effect of the vapor residence time. So during the pyrolysis process of the biomass, it is formed significant amount of the vapor. Now this pyrolysis vapor can suffer secondary reactions through thermal cracking or depolymerizing or recondensation of the charred residue, which leads to decrease in the bio-oil yield. So we need to minimize the secondary reaction through the rapid removal of the vapor from the reaction zone. There are several studies. They analyze that the nitrogen flow inside the reactor, they increase the flow of the inert gas, causes an improvement in the bio-oil yield. However, if we increase the flow rate of the inert gas, the liquid yield will reduce, because there will be not completion of the condensation reaction of the vapor, so increases the ultimately gaseous yield in the process. Higher temperature in a longer residence time are suitable, perfect for oxygen free bio oil production. Now coming to the effect of the reaction time and feed rate of the biomass. In longer reaction time can happen secondary reactions of the pyrolysis of the vapor, so that can cause the lower bio oil production. So we need to optimize the reaction time. When the feed rate of the product distribution and the bio oil characteristics entirely dependent on the reactor configuration. So under higher feeding rate, the vapor residence time will be shorter, meaning that uh, secondary cracking or secondary reactions will not be favorable. So we will get a more quantity of the bio oil and less quantity of the char or gaseous product. But very high feeding rate of the biomass also may cause decrease in the biooil production, because we are not allowing uh, the required residence time for the overall conversion. So bio oil yield will be reduced. So we need to go for optimization of the process to overall um, increase the bio oil yield. So we can say that through the research we have found out that a high bio oil yield could be obtained in the temperature range of 500 with a higher heating rate, a smaller particle size, and low holding time. So next, we are going to discuss about the hydropyrolysis process. This process is also an advanced process for the production of the bio oil. Specifically, this hydropyrolysis is conducted in the range of 300 to 550 degrees Celsius with a slower heating rate. In a ballistic heating rates of flash pyrolysis, the products are rapidly removed from the system when a high hydrogen atmospheric temperature is maintained inside the reactor. So catalysts are very important for this hydropyrolysis. Different catalysts like zeolite and different other catalysts are used in the process for breaking down the complex organic molecules, while it minimizes the char formation and maximizes the bio-oil yield. So, on shortcoming of the conventional pyrolysis is that bio-oil produced will is rich in oxygen content that we were discussing in last slides. But in case of the hydropyrolysis, it produces the bio-oil with reduced oxygen. It can also increase the volatile yield and the proportion of the lower molar mass hydrocarbons in the pyrolysis product. So its higher volatile yield is attributed to the hydrogenation of the free radical fragments sufficient to stabilize them before they repolymerize and form the char. So the bio oil produced by the hydropyrolysis process, it is having greater characteristics, like it is having lower acidity, lower viscosity, higher hydrogen by carbon ratio, and making it more stable and easier to refine into transportation fuel. The advantage of the hydropyrolysis is that it is producing high quality product at a maximum liquid yield. But it is having also some disadvantage, like high hydrogen consumption is occurring in the process. So the high processing cost is involving, and this is only a short term economic consideration. If the hydrogen from the carbon free source become most competitive, cost competitive, the hydropyrolysis can become commercially exploitable technology for the conversion of the lignocellulosic biomass with complete utilization of its carbon content. Now at the last we are going to discuss about the applications of the bio oil. So bio oil, we know that it has several terms of applications. It can also use in the boiler fuel in comparative to the heavy fossil fuel. The combination of the bio oil features with the low emissions of the carbon dioxide shocks NOx. So they will reduce the air pollution, mitigate the problem that is related to the shocks NOx emission from the boiler. So there has been a study that confirmed that co-feeding 2.58% of the bio oil with the fossil heavy fuel, the concentration of the shocks and NOx they may reduced this percentage respectively. So there is certain percentage of the co-feeding of the bio oil with the already existing heavy fuel oil. So there will be, we can have reduced emission of the shocks NOx. Direct burning of the bio oil, aiming for the heat production that could be competitive with the fossil fuel resources supply economically. While using the bio oil as a boiler fuel, proper pumping of the bio oil, ratio of the air flow rate to the bio oil flow rate, nozzle design, they could change the efficiency of the boiler significantly. However, due to distinct properties of the bio oil that we discussed, like higher acidity and higher oxygen content, and those kind of shortcomings that we already discussed, so from that distinctive properties, these configurations of the burner should be redesigned when we use the bio oil as a fuel. In addition of that, the solid particle matter present in the bio oil should be reduced or should be treated through the filtration process, especially in the combustion chamber, to collect the ash to prevent the blockage. For longer term operation, they conclude that um, researchers has concluded that the bio oil should be ash free. In addition to that, compared to the direct combustion of the bio oil, we can also go for the co-firing. Co-firing of the fossil fuels could enhance the efficiency of the engine, and they reduce the cost of the burner system and all engine body modification. Low co-feeding amount, like less than 5%, the bio oil could be co-fired with different fossil fuels without noticeable harm to the existing furnaces. The bio-oil contains high amount of the acid, water, and heavy oligomer compounds which make it unstable, and it contains lower energy content. As a result, the storage, transport, and direct use of the bio-oil in the engine of the vehicle is very difficult. We overcome this process by the help of this hydro deoxygenation process, which can be employed as a methodology to improve the properties of the bio oil as engine fuel. So this process is a catalytic process which has been conducted under generally high pressure, high reaction temperature condition to reduce the oxygen content in the bio oil. Now, catalytic deactivation is also a great issue when we are using the bio oil as it is, because it may form the coke formation, which is a main problem of the dehydroxygenation process of the bio oil. So, this process require a good catalyst which can reduce the coking and the accelerating, which can reduce the coking and also accelerate the hydrodeoxygenation process. Steam reforming of the pyrolysis bio-oil. These are intensively used to produce the hydrogen from the biomass resources. If the bio-oil instead of the biomass is used as a feedstock for the hydrogen production directly, the transportation cost could be remarkably reduced. So it is beneficial because biomass having lot of volumetric the biomass, the raw biomass is having lot of volume, but if we convert it into the bio oil and then we are going for the hydrogen production through the steam reforming of the bio oil, the overall transportation cost will be reduced. Anyways, the hydrogen produced from the steam reforming of the bio oil is a central refinery could easily do upgrading of the bio oil to biofuels by a hydrodeoxygenation method. Thus, steam reforming of the bio oil is a promising process to obtain hydrogen. Due to quick formation of the coke, the reactor design plays vital role in eliminating the coke formation issue in the steam reforming process. So, mostly fixed bed and fluidized bed reactor are used in the steam reforming of the bio oil. Different organic chemicals can also be produced using distillation of the bio oil. Generally, we follow the low temperature distillation method, which serves short time of the heating and high efficiency of the bio oil into different products. Bio oil can be fractionated into three components: light component like ketone acid, middle components we get light phenolics and sugar, and heavy components we get high content of the heavy phenolic and sugar fractions. So we also follow liquid-liquid extraction method where different solvents like alkaline solutions, ketones, ether, and supercritical carbon dioxide and hexane, toluene, this kind of solvent we use to extract certain chemicals from the bio-oil mixture. This bio-oil can be polymerized to produce high-strength carbon, followed by densified carbon material by carbonization reaction. This controlled solidification reaction and consecutively the final product properties could be challenging due to the complexity of the bio-oil composition. Now, when we do the distillation, we will get at the bottom of the distillation column, we will get the tar also. Now, the tar produced during the pyrolysis reaction can also be utilized to fabricate activated carbon and other insulation material. We follow vacuum distillation, which is used to obtain the bio-pitch from the tar, and then the bio-pitch is converted to carbon fiber by melting and extruding processes. Subsequently, carbonization of the carbon fiber is performed to ultimately produce the activated carbon. Bio-oil from the pyrolysis of biomass is also used as a binder in the asphalt due to its renewable feature and low content of the heterogeneous atoms such like low content of the sulfur and nitrogen. This biobinder can also be directly used or used as a mixture with the petroleum based binder in the asphalt. We also get wood vinegar, polyurethane foam, pesticides, and plastics. A wide range of product can be derived from the bio oil. So today's class we have discussed a lot about bio oil and biochar. If there is any question regarding today's class, you can ask. In the next class, we will discuss about the bioethanol and biobutanol production. So we will meet in the next class to discuss a lot about that particular product from the process. So if there is no question from today's class, I tried my best to cover all of the important points for biochar and bio oil. So if there is no other question, then we can end this class session here. Thank you for joining. We will meet in the next class.